Good morning. I'm Jaehyun from Sungkyunkwan University. I'm going to talk about the scheme that a secure, fast, and resource-efficient serverless platform with function rewind. This is a joint work with Bumsuk, Minwoo, Byoungyoung, Euiseong, and my advisor, Jinkyu. Serverless computing has gained traction in cloud computing. Major cloud vendors adopted serverless computing. Developers write functions, and each function handles requests from multiple users. Original serverless computing has no security concerns due to following two features. First, serverless functions are stateless. The state of the function disappears after the function execution. Second, functions run in an ephemeral sandbox. When a user sends a request, a function process is allocated, and user private data is generated during the execution. The same applies when another user sends a request. The sandbox isolates the processes handling different user requests. An ephemeral sandbox eliminates the persistence of any data. Therefore, even if attackers try to attack and infect the function process, there are no security issues. This is because the infected process is isolated in a sandbox from the other processes handling other users' requests and disappears quickly. However, cold start overhead degrades performance. This is because initializing a container for each request takes too long time compared to the function execution. Container reuse is a prevalent technique to mitigate the cold start overhead. However, container reuse raises a security problem of quasi-persistence of data. Quasi-persistence of data is the unintended persistence of data, where data within the container should be removed, but remains due to container reuse. Quasi-persistence opens attack opportunities such as data exfiltration and rootkits. The figure shows the code of container reuse, where the function runs within a loop. When a user sends a request, user private data is left within the process. After that, if an attacker compromises the reused container, the previous user's data could be exfiltrated. If another user sends a request to the compromised container, they could be exposed to security attacks. There are two major schemes to address the security issues caused by container reuse. The first scheme is using the fork system call. Fork removes memory persistence through process isolation for each request. The function handler process forks a child process to handle each function request. The function handler code shows the fork scheme. The handler process calls fork when a user sends a request, and user private data is removed by releasing the function process. After that, if an attacker compromises the container, all resources of the finished function process are released, so no attacks affect other users. Another scheme is checkpoint and restore. The state-of-the-art solution is Groundhog, presented at EuroSys 2023. Groundhog removes memory persistence by using checkpoint and restore. Groundhog checkpoints a function handler process before handling any function request. After handling the request, Groundhog restores the function handler process to its checkpointed state, hence the initial state. If an attacker compromises the container, Groundhog restores the compromised process to its initial state, so no attacks affect other users. However, previous approaches do not consider the repeated execution of a function request. The first problem resulting from this is memory space overhead. Groundhog copies all data to the snapshot to recover initial state. However, the repeated execution of the function allows further optimization opportunities for memory space. The second problem is repeated page fault overheads. After function request handling, Groundhog recovers modified data. When tracking modified data, Groundhog clears soft dirty bits. Clearing the soft dirty bits causes page faults when handling next function request. Groundhog restores function process when function execution finishes, and after the restore operation, Groundhog clears soft dirty bits again. Therefore, repeated page faults occur when handling next function request. Fork scheme causes copy-on-write page faults for modified data. When handling request, function generates copy-on-write page faults, causing high overhead due to page allocation and memory copy. In the fork case, every request handling causes copy-on-write page faults because fork removes copy-on-write pages after function execution. Also, in Groundhog, the mmap areas are located after creating a snapshot or after creating a function process in fork scheme can cause overheads, such as page allocation or page faults. This is because both schemes release the memory areas allocated during execution after the function finishes. Lastly, neither technique considers file persistence. Both schemes leave files within the container after function executions. Files can contain privacy-sensitive data, so remaining files can be leaked or maliciously used. To address these issues, we propose Rewind. The goal of Rewind is to provide snapshot and restore schemes for performance and memory efficiency. So Rewind eliminates memory and file persistence. Also, Rewind minimizes memory usage for snapshot and reduces page faults. Previous approaches just recover the function process to the initial state. In contrast, leveraging the repeated handling of function requests is the key idea of Rewind. To achieve the Rewind's goal, there are two challenges. The first challenge is how does Rewind put only the original data of dirty pages to the snapshot? The second is how does Rewind track pages to dirty without page faults? To resolve challenges, we introduced two operations, snapshot and Rewind. The snapshot operation resolving the first challenge takes a snapshot of each page only when a page is about to be dirtied, by using copy-on-write protection and our body page table structure. When a copy-on-write page fault occurs, the page involved in the fault is copied to the snapshot. Repeated function requests are likely to cause page faults at the same addresses, so Rewind keeps pages duplicated in the snapshot and original one. Also, for zero pages, Rewind does not copy them in a snapshot to save memory because they are initialized to zero at allocation. Finally, Rewind keeps snapshot of files. The other operation, Rewind, resolving the second challenge, restores dirty pages to original ones. The Rewind operation just resets pages to zero if necessary. During the Rewind operation, Rewind deletes the memory area mapped to the function process after the snapshot operation. However, in some cases, it stores the pages and related metadata in a reuse area to accelerate mmaps in the next function execution. Through the snapshot and Rewind operations, no page fault occurs and memory consumption is reduced in Rewind. Finally, Rewind restores files to the snapshot. Rewind's memory snapshot and Rewind operations are efficient due to kernel-level implementation. We introduced a body page table to manage the snapshot more efficiently. During the snapshot operation, the original page table is copied to the body page table. At this time, copy-on-write protection is enabled to track dirty data. If a page fault occurs during function execution, the corresponding page is copied to the snapshot because it will become dirty. Anonymous pages allocated after the snapshot operation are not saved in the snapshot. This is because anonymous pages are initialized to 0 upon allocation, so they only need to be cleared to be 0 for the next execution. During the rewind operation, dirty pages are restored by copying the pages in the snapshot. The write permission of the original page table is then allowed to prevent page faults in the repeated execution. Anonymous pages allocated after the snapshot operation are simply cleared to 0, ensuring no security issues. Since write permission is allowed, any write operations do not cause page faults after the rewind operation. For performance optimization, rewind uses a technique of memory area reuse. Additional memory areas can be allocated and used after the snapshot operation. New memory mapping by mmap followed by page fault and page allocation. This overhead repeats on every function request handling. Memory area reuse minimizes page fault overhead of new memory mapping. So rewind leaves pages, page tables, and associated metadata in the next function execution. Pages in the reuse area are cleared to 0 to prevent data leakage. In the repeated execution, when the mmap system call is invoked, rewind minimizes page faults and page allocation overhead by moving the memory area with the same requested size and permissions to the function process. This minimizes the overhead caused by page faults and page allocations. Memory area reuse is limited to anonymous memory because file-backed memory initially contains file data, which can cause data leakage. Lastly, let me explain how rewind deletes file persistence. Rewind saves the file system state of the container to the snapshot and restores the file system to this snapshot state after function execution finishes. This scheme is implemented at the user level on OverAFS, the file system used by Docker. Before explain our scheme, let's briefly discuss Docker's OverAFS. OverAFS consists of the lower file system, which stores the read-only images, and the upper file system, which stores modified files. The upper file and lower file systems are shown to the user as a merged file system. For instance, when updating file C or creating a new file D, these changes are reflected in the upper file system. Rewind adds the snapshot area to the OverAFS. Rewind copies the initial state of the upper file system to the snapshot area. After the function finishes, rewind restores the upper file system to its snapshot state, thereby eliminating file persistence in the container. In evaluation, we address the following questions. The first question is whether rewind snapshot method effectively reduces snapshot size. The next question is how much the snapshot and rewind operations impact function execution time, and how much rewind accelerates function execution time through the memory area reuse. To demonstrate the questions, we compare rewind with 3 schemes. First, a baseline that runs with container reuse, which is not secure. Next, fork uses the fork system call, which is partially secure because it only provides isolation between function processes. Finally, groundhog, which is the state-of-the-art serverless CNR scheme, and it does not care about files. In micro-benchmark experiments, we demonstrate the overhead of rewind, snapshot, and rewind operations. The micro-benchmark performed random read-write operations. The experiment was conducted with all pages of the workload allocated, So the baseline shows the shortest execution time because there are no page faults. Fork shows a function time over 100 times longer than the baseline due to the copy on write overhead. Groundhog shows nearly 90 times longer execution time compared to the baseline because of page faults and an inefficient user-level CNR method. Rewind shows function times similar to the baseline since no page faults occur during execution and demonstrates a short restore time by handling only the pages. In the function latency evaluation, the function bench benchmark is used, which provides serverless workloads. In the figure, Rewind's function latency is similar to the baseline. In fact, in limpack and matrix multiplication workloads, Rewind's latency is even shorter than the baseline. This is because Rewind's memory reuse minimizes the mmap overhead that occurs for each function request. The right figure shows the latency result of file workloads. The figure demonstrates that the latency of all schemes is similar except for Groundhog. Groundhog does not have results for file workloads because it does not account for files. Due to the longer execution time of file workloads, Fork's copy on write overhead is not noticeable. However, since neither the baseline nor Fork eliminates file persistence, both schemes can be compromised by security attack. The evaluation for memory consumption shows the peak legend set size for each of the 4 schemes. For the evaluation, the function bench is used. Fork consumes 22% to 63% more memory compared to the baseline due to copying pages from handler process to function process. Groundhog shows the highest memory usage because it requires snapshotting all the pages of the function process, consuming 115% to 200% more memory. Rewind shows the most efficient memory usage among the schemes addressing security issues. Rewind's memory overhead is, on average, only 11% higher than the baseline in memory workloads due to copying only dirty data in the snapshot. In conclusion, Rewind provides a secure, fast, and resource-efficient serverless platform. By removing quality persistence of data, Rewind ensures security. The snapshot and rewind and memory reuse schemes improve performance. Rewind uses memory resources efficiently by not copying all function data into the snapshot. Rewind is open source and can be downloaded from the following link. Thank you for listening, and let me take your questions.